Welcome to a new video about analog filter design. In this example we will discuss the elliptic response high-pass filter design. We will see step by step our calculations and verify these in SPICE simulations. So our design objective is shown here, an elliptic response active high-pass filter. We will use the state variable filter circuit, and our high frequency gain should be 1 or 0 dB if the filter order is odd. The specifications for this filter design are shown here. We like to have the maximum passband ripple of 1 dB, which is A max, and the minimum stopband attenuation A min must be 50 dB. The passband frequency is here 1000 Hz, and the stopband frequency is 700 Hz. So at this frequency of 700 Hz, we like to have an attenuation at least of 50 dB. And at this frequency of the passband frequency of 1 kHz, we need to have a gain reduction compared to the high frequency gain of 1 dB. So we will see how we can design this circuit so that we meet these specifications. Okay, first the filter order, that is our first step. We look at the selectivity factor, and for our high pass filter design we need to look at the ratio, the passband frequency over the stopband frequency. So that is the 1000 over 700. That is approximately this 1.428, etc. And then we need to use this value in order to calculate or determine from the table what the filter order must be. Now this is also the maximum allowed value for the selectivity factor, so you cannot go above this. You can go down, so it can be, for example, that this is 1.4, that is better, but you cannot go, for example, to 1.5. Now the transfer function for a normalized elliptic response low-pass filter is given like so. Of course we will design a high-pass filter, but we always start with a low-pass filter and then scale it up and transform that to the high-pass filter circuit. This is for an odd filter order and this is for an even order. You see also here the zero frequency, the denominator expression, and when you have an odd order filter you will also always have a real pole, which is then given by this H0 over S plus P. Now this is the table we need to use for this design. You see here the elliptic response normalize again the low pass coefficients, but we will transform that to the high pass coefficients shortly. And this is the passband ripple of 1 dB, and our stopband attenuation must be 50 dB. So looking at this table, which is our design objective, and looking at the table we see here the filter order, some sections, and a lot of parameters as we see that here in the transfer function. Now when I look at it, the selectivity factor here, FR, is given as 1.407, etc. That is lower than this one, so this is actually a nice option. You can of course go down, then make the filter order 6, so NS6, which is then maybe an overkill. But if you go up, which is then 1.9 approximately, which is then not what we want, because then it is above this, so it is maximum allowed. So we will go for a 5th order elliptic response filter. Okay, and then you see also the coefficients here. So we need to use this, and as said before, we can use, and then we need to have a filter order of 5. Okay, now for the parameters here from this table, again normalized for a low pass filter, those are shown here. So we have an H0, which is this column. This is called the pole 0 gain, which is the total pole 0 gain. It's shown here. The stage 1, stage 2, and stage 3, we have a second order, and first order, so together here we'll make a 5th order circuit. See the zero frequency for each stage, the A1 coefficient, the B1 coefficient for each stage, and you also see here the real pole, all of them from this table. So this is the section 1, this is section 2, and this one additional section, which is the stage 3, which makes this real pole. Again, these are all normalized values. So our transfer function again in full detail, again a low pass filter prototype is shown here. You see here again the first order, second order together, which will make then 5th order. Now we can of course substitute everything here just for the completeness. You see here what the transfer function should be. Again, you see here the 5th order elliptic response low pass filters. Okay, of course we need to design a high pass filter, so we come to that point shortly, and these are the coefficients we will use in the actual component calculations. First, we need to select the frequency scaling factor, and that is in this case pretty straightforward by setting the Kf, which is our frequency scaling factor, equal to omega p, which is our 2 pi times the fp, which is this passband frequency. So that will be then 2 pi times 1000 or 2000 pi radians per second. The next step, step 4, is the natural frequency and the quality factor per stage. Now the state variable high pass filter circuit, that is the first stage, and that makes the second order filter. For that we need to first calculate the zero frequency, which is then given by omega z1. And this is right away also the zero frequency for the high pass filter. You see here again the frequency scaling factor divided by the square root of that omega z1 squared, which is this entry. You see also this here, and that will result in this 4310 radians per second. The natural frequency is calculated using this formula, again using the frequency scaling factor from step 3 and the B1 coefficient from here. You see that, and that will result in this 6296 radians per second. The quality factor, that is the next one for the first stage, and that is then using the B1 and the A1 coefficients from the first stage. That will result in this almost 8 for the Q1. The stage 2 is in a similar form. You again use the coefficients here, and the same calculations are done. Now you use here the zero frequency of the second stage. Again, the frequency scaling factor divided by the square root of this coefficient here, and then you get here 2919 radians per second. Natural frequency in the similar form, and also the quality factor. Okay, now we have all the values for the natural frequency, zero frequency, and the quality factors for the first and the second stage. The stage 3 will be a passive RC high pass filter circuit, and the natural frequency of that one is given by this, again scaled up, so denormalized. You see again the frequency scaling factor divided by the normalized pole frequency, which is then this one. That will result in 18,062 radians per second. Now the quality factor for a pure passive RC filter circuit is always 0.5, so that means Q3 is 0.5. So we have now the necessary information in order to calculate now the component values for our circuit realization. So step 5. Our circuit realization will be then this. In this case you see here the 3 stages. First stage here, the state variable high pass filter circuit, and again this complete thing is the state variable high pass filter circuit. And you see here the RC high pass filter circuit, which is a passive RC high pass filter. This is stage 1, this is stage 2, and this is stage 3. So we need to calculate here the components. You see here the primes for the first stage, the double prime for the second stage, and you see here the C7 and the R7 for the third stage. Okay, let's bring it up, and this is now the complete circuit we need to use, and we need to determine all the components. Let's bring up the denormalized values we have determined. So the high pass filter stages 1, 2, 3. You see the quality factors, the natural frequencies, and the zero frequencies. The zero frequency for our passive high pass filter circuit is at infinite, because you don't see zero frequency in the numerator of that expression, so that is always at the infinite. Okay, now selecting the resistors, the R's here. So you see here the couple of R's are here, so 4 R's here, and again the same 4 R's there. We selected the 100 kilo ohm, that is really arbitrary. There are also 2 capacitors here, C, C, another 2 capacitors there, C, C, so all of them are 100 nanofarads. Then we can calculate, using the procedure, the other components. So stage 1, this filter circuit, that is then calculated using this formula. You see here the R1 prime and the R4 prime, they are equal to each other, so these two. And that is then calculated using the quality factor from the first stage, the natural frequency from the first stage, and our selected capacitor. And that is then actually shown here. So you pick this Q and this omega N from the first stage, and of course our 10 to the power minus 7, which is our 100 nanofarads, and you will get here 12.66 kilo ohms. Okay. Now our 2 prime and our 3 prime are also set equal to each other, and this is then given by this expression, and then you see again here the natural frequency and the selected capacitor, and that is then here 1588 ohm. The R5 prime, which is this resistor, is then given by this expression. See here the R we have selected, the Q1 from this stage, the zero frequency for the first stage, which is this, and the natural frequency. So if you substitute here again, you get here 23.61 kilo ohm. Now it was required that we have a high frequency gain of 1. So if the filter order was odd, now we have a fifth order, so that means n is 5, so it is indeed odd. So that means we need to choose for k of 1 in total. Now this is the first stage, so we select k1 is 1. And that is then, using the formula here, we can calculate now the R6 prime, which is shown here, and it will also be then 100 kilo ohm by using this formula. Now, next part, stage 2, is really similar. The only change is just the index. So you go now to the Q2, omega N2, etc. and also do the double primes for the resistors R1, R4, etc. Now, similar form, you take the values from the table and calculate that. It is really a copy of that one, just a change of the index and the primes. And then again, we select the K2 here as 1 again, because we need to have an high frequency gain of 1. So that means R6 double prime here will be also 100 kilo ohms. The final one is all stage 3, that is our passive RC high pass filter circuit. Now our natural frequency here should be then 1 over the product of the capacitor and the resistor here, R7 times C7. And now we have a choice because we have two unknowns, so we can select this capacitor as, let's say, 100 nanofarads. And then we can calculate the R7 using this. You see here the again natural frequency from the table, and that will result in 553.6 ohms. Okay, now we have everything, so we are done. So we can now check the simulation circuit. This is now the circuit in the Tina Ti SPI. You see here all the components and the operational amplifiers, the input here, and we measure all the way here at the output. This is now the full 5th order elliptic response high pass filter circuit. Okay, let's now go to the simulation results, the Bode plot. This is the gain plot. You see here now in blue the gain. You see indeed there is a ripple here in the passband, and there are two notches because of the 5th order effect in the stopband region. Now let's go one by one. The high frequency gain is indeed 0 dB, so this is indeed as expected, as wanted. And at 1 kilohertz, which is our passband frequency, the gain is indeed minus 1 dB, which is then going down from this baseline by 1 dB, which is indeed as we wanted. We also see at 700 hertz that the gain is minus 55.8 dB, which is more attenuation than the minimum required of 50 dB. So this is also as we wanted. Now we have here two notch frequencies. This is at 464 hertz approximately, and that is really the zero frequency of the second stage, which was in the radians 2919 radians per second. And if you convert that, you get this value, which is very close to what we see here is in the simulations. The other notch frequency is here at 685.8 hertz, and that is then the zero frequency of the first stage, which you see that here. And if you now also calculate that in hertz, you see that that is really close to what we have in the simulations. So it is as expected and according to specifications for our high frequency gain, the passband frequency, and our stopband attenuation. Now let's now zoom in the passband ripple region in more detail. You see here again the ripple. This is just the passband region. You see clearly that there is a ripple in the passband region. That makes actually the elliptic response more useful in order to create filter with a lower order. You see that again the high frequency gain is 0 dB and a passband frequency of 1 kilohertz and a gain of minus 1 dB. This distance here is indeed 1 dB. That was our example considering the elliptic response active high-pass filter circuit. We have calculated our component values for our state variable filter circuit and used the SPI simulations to verify our calculations. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.